How's it going, ladies and gentlemen? Mr. Donahue here again. This time we're going to take a look at practice problems for further applications of ideal gas equation. So this is going to be an equation we're going to end up using, and it's from the PV equals nRT. And then we also know that moles equals grams over GFM, or the gram formula mass. So if I substitute that in, I get PV equals grams over the gram formula mass times RT. And from that, we can figure out density or the gram formula mass and that kind of info. So if we take a look at number one, it says a 2.49 gram sample of a gas has a volume of 752 milliliters at 1.98 atmospheres and 62 Celsius. So which of the following options could be the identity of the gas? So the real question that we have to solve first is, what is the gram formula mass of this gas? So I know, hey, PV equals nRT. And I also know that N is grams over the GFM. So I get PV equals grams over GFM times RT. And in this case, I want to solve for the gram formula mass. So I do a little substitution. I got to multiply both sides by GFM and divide both sides by pressure volume. So I end up with the gram formula mass equals the grams times RT over the pressure times the volume. So now if I plug and chug those numbers in, I got 2.49 grams times R. Well, if I'm using atmospheres, it's got to be that 0.08206 liters atmospheres over mole Kelvin times the temperature in Kelvin. So 62 Celsius, I have to convert to Kelvin. At 273, I end up with 335 Kelvin. And then divide by the pressure times the volume. The pressure, they said, is 1.98 atmospheres. And the volume is 752 milliliters, but I got to convert that to liters, so it's 0.752 liters. And when I plug and chug, I end up with a 45.97 grams per mole. So now I got to look, well, which one of these options is going to give me a gram formula mass of, pretty much that. And the best one is going to be NO2. It's the closest gram formula mass to the one we just calculated. So that could be our gas. Number two, what is the density of neon gas at STP in grams per liter? So again, I got PV equals nRT, but I also know that the moles is equal to grams divided by GFM. And if I want grams per liter, I gotta times the GFM over here to cancel it out there, and then divide both sides by RT to get rid of RT on this side. And now I gotta divide each side by volume, so I get grams per liter. And now I go, hey, all right, I got grams per liter. I don't really care how many grams they are or what the volume is. It's saying the ratio of grams per liter is GFM times pressure over RT. So I go, the GFM of neon is 20.18 grams per mole times by the pressure. At standard pressure, it's 1 atmosphere, divided by RT. For atmospheres, it's 0.08206 liter atmospheres over mole Kelvin, and my standard temperature is 273 Kelvin. When I plug and chug and I do all that math, I end up with 0.901 grams per liter. That would be my final answer. All right, number three. What is the density of NO2 in a 4.5 liter tank at 760 torr and 25 degrees Celsius in grams per liter? So same process. I got PV equals nRT, but N is really grams over the GFM times RT. And if I'm trying to get grams per liter, I got to divide both sides by RT. Cancels that out, times each side by the gram formula mass to cancel that out, but then divide both sides by volume. Cancels that out. So again, I end up with gram formula mass times the pressure over RT should equal my grams per liter. So all right, GFM of NO2 is roughly 46.01 grams per mole times the pressure. Well, they're saying 760 torque over RT. The R, if I'm using torque, is at 62.36 liter torque over mole Kelvin. And the temperature, 25C in Kelvin, is 298 Kelvin. So when I plug and chug, beep bop, boop, I end up with 1.88 grams per liter. And if you take a look, moles divided by moles cancels out. Kelvin times Kelvin over there cancels out. Torr divided by torr cancels out. I'm left with just grams per liter, which is what they were asking for. Also, my units tell me I did the right thing. Number 4, what is the molecular weight of a gas in grams per mole if 6.7 grams of the gas occupies 6.3 liters at STP? So we're trying to get the molecular weight, or the GFM. So again, I got PV equals nRT, but N is really grams over gram formula mass times RT, and they're asking me to solve for the gram formula mass. So I multiply that to both sides, I get GFM, and then I got to divide both sides by PV. So I'm left with GRT, but then I divide each side by PV. I get gram formula mass equals grams times R times temperature divided by pressure volume. So now I can plug and chug. It says, hey, 6.7 grams times R. I guess I get to take my pick. I like atmospheres. So I'm going to do the 0.08206 liter atmospheres over mole Kelvin for my R times my temperature. Let's see, it says at STP, so standard temperature is 273 Kelvin divided by standard pressure, 1 atmosphere. And the volume they tell me is 6.3 liters, so times 6.3. So now I can pick up my calculator and do some plugging and chugging. Beep bop, boop. To 2 sig figs, I get 24 grams per mole. So there you go. All right, number 5. How many liters of hydrogen gas can be produced by 4.33 grams of zinc reacting with excess sulfuric acid at 38C and 763 torr? So first step, hey, what is this equation? We're making H2 gas by zinc reacting with sulfuric acid. And you go, all right, well, I'm making H2 gas. And what's left over, it's going to be zinc sulfate. And it looks to be balanced, which is nice, so that's nice. So first, let's break it down. First thing we're going to have to figure out is, zinc. We got to convert that to moles. They told me grams, but how many moles of zinc is that? Once I know moles of zinc, I can go, hey, what's my zinc to hydrogen gas ratio? If I know how many moles of zinc I had, I can figure out how many moles of hydrogen gas I can make. Now, once I have that, I go, all right, if I know moles of H2, now I can PV equals nRT it to solve for my volume. All right, so let's figure this out. 1, zinc. It says I have 4.33 grams of zinc. And the GFM for zinc is, what is it, 65.38. So I know that 1 mole is 65.38 grams. So when I plug and chug that, I end up with 0.0662 moles of zinc. Now my second step is going to be, all right, now I know how many moles of zinc. What is my zinc to H2 gas ratio? This one's nice, it's a 1-to-1, so I know that I also am going to make 0.0662 moles of H2 gas. So the next step, third, now I got a PV equals nRT it. Let me do some algebra. My volume is going to equal nRT divided by P. So now I can plug and chug. My N is at 0.0662 moles times my R. Let's see, I'm using torr in the problem, so it's going to be that 62.36 liter torr over mole Kelvin times my temperature, and I'm running out of room there, so I'm just going to have to write it up a little bit. My temperature is 311 Kelvin, right? They gave me Celsius, convert that to Kelvin, divide by the pressure, 763 torr. When I do that, all my units cancel out except for liters, and I end up with 70.9 grams. Oh, not grams, liters. I'm sorry, I'm looking at the wrong problem. Preview, that's the next problem. This one, we end up with 1.68 liters. Total liar until right now. Now I'm telling the truth. It's 1.68 liters. All right, number 6. Airbags in automobiles use decomposition of sodium azide as their source of gas for rapid inflation. Here's the balanced chemical equation. How many grams of NaN3 is required to provide 40 liters of nitrogen gas at 25 Celsius and 763 torr? All right, well, let's break it down. First thing, what are they telling me? They're telling me the volume that I need, the temperature, and the pressure. So first step is like, hey, all right, I'm probably going to need to use the PV equals nRT, and I'm going to use that to solve for the moles of N2 gas. Once I know the moles of N2 gas, I can take a look at the balanced chemical equation and go, hey, what is my ratio of N2 to Na3? So I can figure out the moles of Na3. And then last step, they don't want moles, they want grams. So I just convert the moles of NaN3 to grams. So let me do the first step. PV equals nRT. All right, I'm solving for N, so I know N equals PV over RT. So the pressure, they tell me is 763 torr times the volume. Well, that's got to be 40 liters from the problem. Divided by RT. If I'm using torr, I need to use the 62.36 liter torr over mole Kelvin times by the temperature in Kelvin. Well, let's see, 25C is 298 Kelvin. So when I plug and chug and I do that math, I end up with 1.64 moles of H2. All right, so now I have to go, hey, number 2, second step, my moles to mole ratio. So the NaN3 to H2 is a 2 to 3 ratio, and my 2 is the unknown. I'm trying to figure out how many moles of that is, and my 1.64 moles is the H2. So here I solve for the moles of NaN3 by cross multiplying and dividing, and I end up with 1.09 moles of NaN3. So now third step, running out of room. I'm gonna erase all this stuff. Sorry. All right, number 3. Third step. Now I just got to convert grams to moles. So I go, hey, 1.09 moles times the gram for mass of NaN3, which I did off screen. It's 65.02 grams per mole. So when I do that math, I end up with 70.9 grams. Now, if you didn't round, if you set all of these steps up into one equation, you would have gotten like 71.2. And the reason for the difference is the rounding with the in-between steps. So anything in there is kind of justifiable. All right, I hope you found that helpful. I'll see you in class. Okay, bye.